Greetings and salutations, magical chemists. Let's go ahead and review basic mole calculations. But first, before we get to the math, we should review some terminology. There are different types of particles that are very tiny, and thus we will use the mole to calculate them. But it's good to know them by name. First, if you have a single part of a single element, well, that's an atom. However, if you're talking about something with a charge, positive or negative, it's going to be an ion. Units of a covalent compound are considered molecules, whereas ionic compounds are called formula units. An important note I'd like to make here is that diatomic elements, you know, those delicious Brinkelhoff elements, those are considered molecules because they are two atoms covalently bonded. Now that we've got that out of the way, let's go ahead and talk about how the calculations might work. First, below you'll see a generic mole map. If you're trying to convert between any of these particles and how many moles, well, by definition, there are 6.022 times 10 to the 23rd things in 1 mole of that thing. Just like there are 12 things in 1 dozen of that thing. It's just a much bigger number because, you know, atoms are much smaller than eggs. We also, I am sure you remember the fun and excitement, we can convert between the moles of something and the mass in grams. That's using the molar mass from the periodic table. Let's try a couple of practice problems together and we can see if you remember. Now, if you are just like, I got this, I remember chemistry, then honestly, you should be able to do all of these. You can go ahead and try them, and when you're ready to check your answers, unpause the video. But if your brain's a little fuzzy, don't worry, I'm going to go ahead and walk through these as well. So let's take a look at the first one. If you want to try it on your own, pause the video now. Okay, we are trying to find the mass in grams of 1.60 times 10 to the 24th molecules of this lovely B3Br6. What is that, triboron hexabromide? Well, okay. You want the mass in grams, you have to have the molar mass. And if you need the molar mass, you need the periodic table. So let's take a look. Okay, if you want the mass in grams of 1 mole of B3Br6, well, first you got to figure out the mass of boron, B. Well, if you look on your delicious periodic table, boron individually has a molar mass of 10.81 grams. So you take that amount times 3, because there are 3 of them. Next you find bromine. Well, bromine, a little bit heavier. Each individual one is 79.90. You multiply that times 6 and add it to the 3 borons. And when you combine all those masses together, if your calculator loves you, you'll have a molar mass of 511.83 grams per mole. The good news is you don't have to show out this work. You're allowed to just use the number you get. Just make sure you get the right molar mass. So let's take this information back with us to our problem. Okay, we've got the molar mass, or molecular weight. We're not in physics, so we'll call those the same thing. And now, we can't start there, though. You might remember mole calculations as one of the first times we introduced you to the glories of dimensional analysis. You know, piles of fractions, unit conversions. So, in a unit conversion, you always want to start off with the units you're given. In our case, molecules. Now, before we can convert to grams of this molecule, we need moles of this molecule. So we need Avogadro's number as our conversion factor. But it's important to know, you're like, wait, what am I multiplying or dividing by 6.022 times 10 to the 23rd? It's a big difference. The key, the beauty of dimensional analysis, is that whatever unit you have on the top, that's the unit that carries down to the bottom of your conversion fraction, and that's how it cancels out. Now, in this conversion factor, if you're converting between molecules and moles, moles being the #1 most important unit in all of chemistry will always get a 1 next to it. So in 1 mole of anything, you would have Avogadro's number of particles. Now, in calculations, as people are practicing, I do know a lot of people who will do things like say, Avogadro's number, because writing out 6.022 times 10 to the 23rd every time takes time. However, I do not generally do that, because on a test, you cannot do that. That is not an acceptable abbreviation unless you have defined it. So I will generally write it out in full using E as a tiny abbreviation. Now that we're in moles, we have our molar mass as a conversion factor to convert from moles to grams. Once again, we're taking the unit from the top and carrying it to the bottom. So moles are on the bottom, grams are on the top. Once again, converting between moles and anything else. The mole gets a number 1, and we've already calculated in 1 mole of this lovely compound, we will have 511.83 grams. The rest is just math. And notice the glory. Molecules is on the top, molecules is on the bottom. It is dead to us. Moles is on the top, moles are on the bottom, also dead to us, leaving us just with grams, which is the unit we're looking for. Now, mathematically, when you're trying to multiply fractions, you basically multiply all things on the top, multiply all the things on the bottom, and then divide. I do that all in one step, but you just have to be careful of mathematical order of operations on your calculator. And once you plug that in, your calculator will spit out an answer. But we're not quite done with the fun and excitement, because sig figs are still a thing. Notice on your given number has 3 sig figs. Only the numbers in front of the times 10 to the are significant. So that means you need to round your final answer to only 3 sig figs. Oh, well, that means the 9 is going to bump up that 5. Now be careful, because I get a lot of people that tell me the answer would be 136. But this was 1,359. You can't change the order of magnitude. So we're just going to go ahead and put a 0 there. And now, hey, look, we've got 3 sig figs, just like we needed. Of course, we also need to put our units in chemical. And then it is always considered good form to put a box around your final answer so your poor graders can see what you've done with your work and find what you intend to be your final answer. Okay. Hopefully that has reminded you about all the fun and excitement. I would like you now to go ahead and attempt the second one, and even better, the third one. I'm going to go much faster through the rest of these, so you need to try it on your own. Unpause the video when you are ready to continue. Question number 2 wants to know how many moles of nitrogen gas are found if you had a sample of 57.2 grams. The trick here is to remember Brinkelhoff. You are converting 57.2 grams of N2 into moles, and that is actually just one quick conversion factor. Because we're starting in grams and going to moles, this time we're dividing by the molar mass, and it is nitrogen gas, so it's not 14.01 grams per mole, it's 28.02. So keeping the 3 sig figs we started with, that gives us 2.04 moles of N2. All right, another one. How many formula units of magnesium carbonate are contained in a 2.34 mole sample? Well, I know formula units tends to screw with people because honestly, a lot of chemists even ignore the term formula units. We just talk molecules of this, molecules of that, but that is not technically accurate. And the AP chemistry test is all about technicalities. Yum. So here, one of the things to think in your brain to make it sound less weird is just like, oh, it's like they want to know how many molecules there are. And that just means it's an Avogadro's number conversion. But of course, technically, they are formula units because magnesium carbonate is ionic. In this case, we're multiplying by Avogadro's number because formula units are a tiny particle. You'd expect a large number of them. And indeed, that's what you get. 1.41 times 10 to the 24th formula units. Okay, so those are basic mole calculations, but chemistry can always get more fun. We can add a little bit of a twist, so let's take a look. It turns out you can actually do mole conversions using the ratio shown in a chemical formula. This allows you to convert from the entire compound to atoms or ions, or even electrons or protons, found within that compound. It basically is just another conversion ratio, another mole ratio. Now, these problems do tend to be heavily missed on tests because oftentimes people will miss that extra step of going from the compound to, say, how many atoms of oxygen in the compound. So here's something to be on the lookout to help remind you that you're going to need to go that extra step. If the problem gives you a compound, but asks for atoms or ions, then you need an extra conversion factor. Let's take a look at a sample calculation so you can see what in the world I'm talking about. In this first problem, a student measures out 2 moles of a lithium phosphate, and we want to know how many moles of lithium ions are in that sample. Now, at first blush, this can be confusing. You're like, moles? Are they actually asking me for something? But you're going to notice. You're going to notice that they gave you a compound, they gave you the whole thing, and they're asking you about a part of it. So we're converting from the entire compound to just the ions specifically of lithium. So we're going to use the chemical formula for our mole ratio. You might be thinking, but how the heck am I supposed to find this conversion factor? It's not like stoic, I don't have a balanced reaction. It's not like they're giving it to me somewhere else, but they are giving it to you. They are giving you the answer within the chemical formula itself. Within this compound, for every one compound unit, we will have 3 lithium ions. So the key is when you're doing a part-to-whole conversion, the whole thing always gets the number 1. You're looking at one whole thing, and then the ratio becomes to some number of the part inside. So ultimately, you're really just taking your given times 3, and that's it. But it's very important. The question of do you multiply by 3 or divide by 3 often screws with people. And so the dimensional analysis will make sure that you know exactly what to do. Okay, this next one is a glorious practice problem that I would like you to try independently. It does involve something sneaky. Pause the video if you don't want to know the sneaky bit. But otherwise, I'll give you a warning before you try it. This is a 5.56 milligram sample of Freon, which is just that chemical. And you want to calculate the number of molecules of Freon. So please pause the video, try on your own, and when you're ready to check the answer, and it's just going to be the whole answer, unpause the video. So let's see what happened. First, to do this problem, you had to remember how to convert from milligrams to grams. Those metric conversions are still a thing, and you do need to remember the basic ones. They will not be given to you. So it turns out there are 1,000 milligrams in 1 gram. Once you are in grams, then it's easy enough to use the molar mass to convert to moles, and then Avogadro's number to convert to molecules. Some of you who are paying close attention might be wondering something right now. In the problem up above, I had a number, a unit, and a chemical for all of my parts. Number, unit, chemical, which is very important if the chemical or the part is changing. So if you are converting from a whole to a part, like we did with ions, or a part back to a whole, then you need to label that because it's changing. But you notice, when we were looking with Freon, well, it was Freon the whole time. So I generally don't label the compound if the compound remains constant. You certainly can, and it looks prettier, but it takes longer to write. And AP is a timing game, unfortunately, but true. Okay. So there are 3 more practice problems for you to try using variations of these mole calculations. If you take a look, it would be a great idea to try each of these problems and to see if you understand how to apply these mole calculations. I am not going to put the full-out answers here, the worked out solution, but I do want to give you the final value so you will know if your math is correct. And of course, the full answer key will be posted online as always. So let me go ahead. I'm going to give you the answers to these 3, and then it is a really awesome idea for you to go ahead and try to work these out on your own. And there you have it. Thank you for playing with moles and the glories of chemistry.